So my name is Eric Pollet. I come from the University of Strasbourg, and I will talk about novel systems and we have developed recently on thermoplastic polysaccharides, mainly based on starch and chitosan materials. So maybe I will quickly pass quickly about this. Where is Strasbourg? Quite famous city for the European Parliament. Cathedral and some wine, beer, and food stuff. It's quite large university, 40 to 50,000 students, 3 main campuses, and mine is this one at the northwest. University ranked in 17th position in chemistry, so this is one of the main activity in Strasbourg. So I'm teaching and doing research at ECPM, which is an engineer school from the University of Strasbourg, preparing students for an engineer master degree in organic chemistry, materials, and polymer chemistry also. So, and we have the Institute in Chemistry, Processes for Energy, Environmental, and Health. And in this institute, the Department of Polymer Engineering, which is here, consists in 2 groups, and our group is the bio team. We have 4 permanent staff members, Professor Luc Averus, which is the team leader, another professor, Jean-Marc Yelt, which is not doing research anymore, but more the vice president of the university, and Vincent Philippe as associate professor in biotechnology, and myself in polymer chemistry. So we have at the moment 3 postdocs, 8 PhD students, and 3 or 4 master degree students. And the topic of our group, our main investigation area, is the non-food valorization of biomass for the elaboration of polymer materials. And we develop bio-based and or biodegradable polymers, mainly for environmental and biomedical application. And doing this through an integrated approach, starting from the biomass, so involving biotechnology, biochemistry, bioproduction of monomers, then chemistry, chemical synthesis, modification, leading to polymers, and formulation and process of these polymers up to the final object. So this is our approach, which corresponds to basically the well-known biorefinery concept. And here are a few examples. If we take biomass from plant, from fractionation, for instance, we may recover starch by fermentation, leading to sugar, as we have seen before, leading to PHAs, for instance, PLA, or directly transforming starch into thermoplastic starch, as I will show later. From lignocellulosic compounds, for instance, we try to develop new materials based on lignins and tannins as bio-based building blocks. From seeds or vegetable oils from seeds, we also prepare bio-based thermosets or thermoplastics compounds. From other type of biomass, like crustaceans, waste of shellfish, mushrooms, chitin and chitosan are extracted, and I will show later on the biomaterial based on thermoplastic chitosan. And also, with the fiber, lignocellulosic fibers, one may develop composites, biocomposite material from natural clay minerals, also other types of nano biocomposites, as I will discuss later. So first topic, I will talk about starch and plasticized starch, and then different types of multiphase systems, materials based on plasticized starch. So first, let's talk about starch materials. As most of you may know, starch is a main storage energy for vegetables, main storage raise of carbohydrate for higher plants. Industrially, starch is mainly obtained from corn in North America, in the US, from cassava in Asia and South America, and in Europe it's mainly from wheat and potatoes. It's a fully biodegradable compound, so coming from renewable resources, produced in large amount, between 50 to 60% dedicated to food application. That means also that almost 40% of the produced starch is used for non-food application. And it's quite cheap material. Native starch is prices slightly below 0.5 euro per kilogram. And interestingly, as we will see just after, starch can be processed using typical processing devices for plastics. So starch, as you may know, is composed of two macromolecules, amylose and amylopectin. And I will not go into a lot of details, but just say that amylose is mainly the linear polymer with sugars with alpha 1,4 bonds, and not a lot of branches. So mainly linear, around molecular weight around the million Daltons. While amylopectin is a highly multiple branch polymer. Still around 95% of sugars with alpha 1,4 bonds, but around 5% of alpha 1,6 that you have here responsible for this branching. So it's a highly branched and gives to starch this specific grape structure, where the amylopectin clusters from here, and here you have branching and amylose chains on the other side. So depending on the botanical source, this ratio between amylose and amylopectin may vary a lot, and also from one type of vegetable, one type of plant, it may also slightly vary depending on the place it has been grown, on the climate condition, and so on. So here you have a few examples where you can see that wheat starch contains about 25 to 30 percent in amylose, and slightly more than 70% amylopectin. But waxy starch, for instance, you can reach up to 99% of amylopectin and almost integrally amylopectin. And amylomaize, it's up to 80% of amylose and lower content in amylopectin. We always have a few amounts of lipids and proteins in starch, and these proteins are responsible for Maillard reactions that give this browny color to bread when you cook it, for instance. And some water content, depending also on the botanical source and the condition of growth of the plant. Starch appears as granules in the plant, and also depending on the botanical source, you may have a large variety of shapes and size. Here you have microscope photos of wheat and pea starch granules. And this granular structure of starch is represented, is shown here. You have this organization, radial organization from the hilum of the granule, with the macromolecules mainly oriented according to this radial axis. And the superstructure of the granule is made of these inter-macromolecular hydrogen bonds between the OH groups of the chains, and also water molecules. And as previously mentioned, amylose and branching regions will give the amorphous regions, rings, whereas the amylopectin cluster will form these crystal strips or lamella. Here you have pictures of this granular structure and like an onion ring granular structure of the starch granules. Here you can see, for instance, a microscopy of starch that has been submitted to amylase enzymes, so degrading amylose and leaving the amylopectin crystalline parts here. So from this granular native starch, we will see that we can obtain different materials depending according to the water content and the thermomechanical input we give, and to destructurate the native starch granules. So it may lead to different types of materials and application depending on the water content and the destructuration level you have. If you have not a lot of destructuration level, low water content, you have almost no transformation of the starch granule. You can use it as a filler to reinforce some plastics. Here, high water content, low destructuration, it's a bakery food application of starch. Here in the middle, expanded starch that you may find to replace expandable polystyrene for packaging. And here what we'll be more interested in is the plasticized starch, high degree of destructuration with quite limited water content. So plasticized starch is not something new. The first works and patents and papers on plasticized starch or thermoplastic starch started on the late 80s. And I said before, to destructurate the granular structure of starch, you need thermal and mechanical input. But the main issue is that the melting temperature of starch is higher than its degradation temperature. So you need to use the plasticizer, the best one being water, but it's a volatile plasticizer. So we also use a non-volatile plasticizer like glycerol or sorbitol that will allow to obtain the so-called thermoplasticized or plasticized thermoplastic or plasticized starch. Sorry. So this is one of the processes that can be used or we have developed to obtain plasticized starch. It's the first step is a dry blend step, which is very similar to the dry blend process you have for plasticized PVC. That means we start with the native starch powder, add the non-volatile polyol plasticizer, typically glycerol, and then recover the dry blend that we put in a mixer, for instance an extruder, with some water, and with the shear and heating we have the fragmentation of the starch granules and its destructuration, plasticization, and hopefully we obtain an homogeneous molten phase. And by controlling the shear and the temperature, obtain plasticized starch, trying to avoid the depolymerization or degradation of the starch. So here, that's the powder. We start with the dry blend, and then we recover the plasticized starch as pellets that we can then process again, blend with all the materials, characterize and so on, as we will see just after. So depending on the amount of non-volatile plasticizer of glycerol, the properties will strongly be influenced, may vary. Here you have wheat starch with different content in glycerol as plasticizer, 14, 25, 35, and up to 50% compared to starch. And you can see that the TG varies a lot, and also the mechanical properties. With 14% of glycerol, you have here quite high modulus, but very low elongation at break, very brittle materials. And if you increase the amount of glycerol, of course you decrease the modulus and increase the elongation at break, with the best compromise for this system being around 25% of glycerol, for which you keep quite interesting modulus, but with the highest elongation at break. So plasticized starch by itself, it's quite interesting already, has interesting mechanical properties, but for some application, these mechanical properties may not be appropriate or enough, and then that's why we also have developed multiphase systems to have mechanical properties matching the requirements for different application. So I will show you a few examples of such a system based on plasticized starch, and what we call this multiphase system. So it's simply by association strategy. So for instance, starting from the plasticized starch, you may blend it with other biopolymers, biodegradable polymers, obtain blends, multi-layers films, for instance, or by addition of a filler or a nanosite filler, obtain biocomposites or nanocomposites. And this by typical plastic processing processes like extrusion, injection, or compression molding. So a lot of different structured materials types that can be elaborated through this strategy. I will show you for starch material examples on nanobiocomposites based on plasticized starch. So what is nanobiocomposite? What do we call it? Nanobiocomposite. It's a biopolymer, here plasticized starch, in which we disperse, add a nano-sized filler, and resulting in this nanobiocomposites. So it may have a lot of different application. And these nanofillers, you may found or use different types of nanofillers that you can classify depending on their morphology. For instance, the first family will be lamellar nanofillers like clays, for instance, but you can also have spherical nanoparticles like nanosilicate or nanometals particles, or also fibers or tubes, here are carbon nanotubes, for instance, or whiskers from cellulose or chitin, which are the whiskers of the crystalline parts of the cellulose. But I will only talk about lamellar nanofillers, and we were more interested in natural clays, and the most common one is montmorillonite. So having this lamellar structure and nano-sized filler, since the thickness of one single platelet, it's around 1 nanometer thick, and for lengths varying from 100 to 200 widths. So quite high aspect ratio. The montmorillonite, it's a stack of platelets, and if you can reach full exfoliation of these nanoplatelets individually in the polymer matrix, you may reach quite high specific surface, several hundred square meter per gram, if you exfoliate totally the clay, which is usually the main objective when you elaborate such a nanocomposites. So we have prepared a nanocomposite based on plasticized starch, first using the so-called unmodified clay, the sodium montmorillonite, and by a small angle X-ray scattering, you can see here that you have the typical signal diffraction peak of the clay in pink due to the regular stacking of the clay platelets. And when you mix it with when you disperse this clay into plasticized starch, you see a shift of this peak showing that you have intercalated some species between the clay platelets. You have an increase of the interlayer spacing, which is here in the neat clay about 12 angstrom up to 18 angstrom. So we have intercalated something between the clay platelets, but when looking into details, we have shown that it's only intercalation of the water and glycerol molecules between the clay platelets, because we have here this typical diffraction peak at 18 angstrom. So using non-modified clay, which is hydrophilic but does not show good compatibility with starch chains. Starch chains are not able to intercalate the clay platelets because you have preferential intercalation of glycerol and water molecules. So we have tried and developed a new type of hydrophilic organoclay. So usually you organomodify the clay to match the hydrophilicity or hydrophobicity of your matrix. Typically commercial organomodified clays bear ammonium salt with long alkyl chains, so you can have better compatibility with polypropylene, other polyolefin or polyesters. And here, because starch is hydrophilic, we had the idea to modify the clay using cationic starch with quite small polymer chain lengths, molecular weights. So this is done in water using ultrasonic baths. So in water, you separate all the clay platelets. The cationic starch adsorbed on the negatively charged clay platelets, and after filtration and lyophilization, you recover your clay organomodified with cationic starch, which has a stacked structure like here. So this allows to have cationic starch chains between the clay platelets, so we are hoping a better compatibility with the starch matrix, and we start with a higher initial interlayer spacing around 25 angstroms, so we hope that the intercalation of the starch molecule will be easier when processing and adding this organomodified clay with the starch matrix. And here are the results we obtained from the small angle X-ray scattering, for which you can see that in pink we have the native, the organomodified clay showing a peak, and almost no peak, no diffraction peak for 1 and 3 weight% of clay in the starch matrix, and a shoulder that is clearly visible here at higher content for 6 weight% of clay. So we think about a well exfoliated structure, nanobiocomposite, and this has been confirmed by transmission electron microscopy. Here you see the dark parts are the ages of the clay platelets, and you see that you can have individual platelets in the matrix and some stacks, but only 4 to 5 clay platelets together, whereas for the unmodified clay you have large dark areas of hundreds of clay platelets stacked together. So good dispersion and exfoliation of the clay, of this organomodified clay in the plasticized starch matrix. And this is interesting for the mechanical properties of the plasticized starch, which has been determined after 1 month, 6 weeks storage at 57 relative humidity and room temperature. And here you can see that when you had the clay, first you increase the Young modulus, the elastic modulus here, because you add a rigid filler in your matrix. But and this increase is higher when you use the clay organomodified with the cationic starch compared to the native clay. So this is the first good result, but most important is the elongation at break value. You see that this is typical when you add the filler, you increase the modulus, but you may also decrease the elongation at break, which is the case with the unmodified clay because of the poor dispersion of the clay inside the matrix. Whereas when using the organomodified clay, which is exfoliated, you have a better dispersion and you maintain more or less the same value of elongation at break, which is quite interesting because the total energy at break goes increasing and is much higher for the organomodified clay compared to the unmodified one. So this was the first series of examples on plasticized starch, and now we'll talk about the chitosan and how we have developed a thermoplastic chitosan in using a similar approach and this also multiphase system based on plasticized chitosan. So quickly, as you may know, chitosan is obtained from chitin, which is the second most abundant natural polymer on Earth after cellulose. It's main components of the cell walls of exoskeletons of arthropods, crustaceans, and also found in cell walls of fungi. And industrially, it's mainly obtained from the processing waste of shellfish. So it's quite similar to cellulose for the plants. And it has also a highly crystalline structure. That's why we can recover chitin whiskers that are the crystalline parts that can be used also as a nanosite filler in some cases. So chitosan is obtained by deacetylation of chitin, and typically for commercial chitosan the deacetylation degree is between 60 and 100%, usually between 90 and 100%. Is the most common values. So chitosan is produced around 2,000 tons per year and has different commercial and possible uses. For instance, in agriculture, because of the as a biopesticide, because of the antifungal and antimicrobial properties of starch, it is used for seed treatments. Starch has also very interesting complexation and flocculent properties, so it can be used for water processing to filtrate water. Also in the beer or wine industry, it can be used. In paint coating for self-healing polyurethane paint coating, and also for biomedical application due to antibacterial properties, can be used for bandage and also for drug delivery or scaffold for tissue engineering application. So regarding thermoplastic chitosan, until 2008, the only way to obtain plasticized chitosan was to do it by solvent casting. And based on what we've developed on thermoplastic starch, we tried to develop the similar approach and to obtain plasticized starch by plastic processing like it is done with a thermoplastic starch. So it's a multi-step process, and in the first step we have the destructuration of the chitosan, and for that we prepare, as previously shown, a dry blend using glycerol with the chitosan, and then to this dry blend we add acetic acid aqueous solution. So we obtain kind of paste that we feed to an extruder or in an internal mixer like we have here. And then this is thermomechanically blended, and at the end we obtain material thermoplastic chitosan, which can be processed again, for instance, to obtain plates for material characterization. So we have developed such a process a few years ago, and then the material characterization has been done in collaboration with the colleagues in Professor Alley in Queensland University, Catherine Dean at CSIRO in Brisbane, and Marie-Claude Dezay at École Polytechnique de Montréal. So first we were interested in the post-processing aging of such chitosan-based material. And here is the evolution of the mechanical properties, the elongation at break with the exposure time or storage time in days at a 57 relative humidity condition. And here you can see that the properties of the materials evolve due to changes in the water content and in the crystallinity of the material. And more or less, very similarly to starch, you have to wait about 1 month to reach stable properties. Here you see a fast evolution important during the 1 or 2 first weeks, and then it's much more slow, and you reach almost constant properties after 1 month of storage. And plasticized starch shows higher differences in evolution due to higher content in water in the material. As you may see here, the storage time and the relative humidity atmosphere at which you store and you make this post-processing aging of the plasticized chitosan may vary with the relative humidity. And here is the water uptake with time. And you see at 70%, 75% relative humidity, you have a fast increase in the water uptake, and then it's more or less constant after 1 week. And the same trends with a lower water uptake for lower relative humidity atmosphere. But you see very important differences in the water content of the material after 1 week, one month. So this will affect strongly the mechanical properties of the thermoplastic chitosan. Here is an example on the transition temperature determined by DMTA, depending on the relative humidity of the storage of your material. And you see that I will not go into detail of all the relaxation temperature, but this one are more, it's more due to glycerol, and this one to chitosan. And you see that it varies a lot depending on the humidity of the storage of the processing aging. And the highest humidity giving the highest water content of the material, leading to a lower TG of your material. So the crystallinity also varies a lot. Here you have the chitosan powder unprocessed, and after processing with or without plasticizer, you see a strong modification, a huge decrease in the crystallinity of the plasticized chitosan, and the crystallinity will be also influenced by the plasticizer content and the type of plasticizer. Here you have the glycerol used as plasticizer and increasing content 10, 25, and 50% compared to chitosan. And you see that the crystallinity decreases together with the glycerol content, and this for the same relative humidity storage atmosphere. I've shown you before materials property with glycerol as a plasticizer, but we have also studied other polyols like xylitol and sorbitol, and these tends to gives higher crystallinity material, and the lowest one being obtained for glycerol. This was not surprising because we have more or less similar behavior with plasticized starch and sorbitol, for instance, which can crystallize during the post-processing ages of the material, induce this crystallization of the plasticized chitosan. So with this plasticized chitosan, we have also tried to develop multiphase system, trying to improve some of the properties of the materials, always with using the same strategy. And we have, I will show you an example of blends and then nanocomposite based on plasticized chitosan. On blends, we have tried to make blends based on plasticized chitosan together with polycaprolactone, PCl, and we obtained the plasticized starch, and it was extruded with PCl. And due to water evaporation, all the water contained in plasticized chitosan evaporate during the processing, leading to a porous structure that could be interesting for biomedical application that have not been tested and studied so far. And as previously shown, we have also developed nanobiocomposites based on plasticized chitosan, always with the same approach, trying to disperse monomarinite clay. And here you see unmodified sodium monomarinite, which gives stacks of clay platelets and not so good dispersion. And using a similar approach that I have shown before, we have modified this sodium monomarinite clay using chitosan but with a shorter chains. And thanks to the cationic groups of the starch, of the chitosan, it can also intercalate the clay and modify it. And this modified clay has been dispersed quite efficiently in the plasticized chitosan matrix and gave quite interesting and good properties with increased modulus and energy at break without reducing the elongation at break, which is a typical behavior of the fully exfoliated nanocomposites, as I've shown before on starch. And finally, to conclude, we have also tested the biodegradability and the aerobic composting of this material. And you see that 95% biodegradation is achieved after 180 days in compost. And that compared to neat chitosan, the addition of glycerol and clay lead to a slightly enhanced biodegradability of these materials. So thank you for your attention. I'm ready to answer some of your questions if you have.